All right. Okay, hello class. Um, I mentioned in the news yesterday that I was having some issues with my internet, and I think I solved the problem so that we can do the two-window setup without it lagging too badly. So let me know if it lags a lot, but I don't think it will. Okay, I think that's better. Yeah, there's a lot of. I got the windows open today. It's a really nice day. The birds are making a lot of noise. Hey Ray, hey Sebastian. One other thing I wanted to say is the Discord has a new section. It's called the recipes section. So if you want to share your recipes of what you've been making during the quarantine, I know that I personally would be interested in taking a look at what you guys are cooking. If you have any family recipes, I'm always looking for more stuff to cook because I enjoy cooking a lot. Okay. Hey Ethan. All right. So let's get down to business. So I was worried that you guys didn't fully understand the lesson from yesterday, so I wanted to do one more example. So what it says is we want to linearize the following relationship and interpret the slope. So P equals V squared over R. So that was the equation for power. This was the equation for power dissipated by a resistor. You might remember it from a couple weeks ago. And I want you to do it in two ways. So if, hey Will, hey Ricky, so if we were to graph power versus voltage. Now, why am I graphing power versus voltage? Because it is the voltage that we're varying, the voltage across the resistor, and then the power changes. We can see that as it is, it's a square relationship. So this graph is going to look like a parabola. You be quiet, Bug! Bug's in the backyard, and he likes to just stand at the fence and watch for He likes to just stand at the fence and watch for other dogs and families to walk by, and then he barks at them. So he's having a great time during the quarantine. He gets to spend all day outside and bark at stuff. Okay. So what we want to do is we want to linearize this graph. So what if I wrote it? What if I wrote the relationship as P equals 1 over R times V squared? All right. Then what if I let Y squiggle equals power and X squiggle equals voltage squared? Then that would put this relationship into the form Y squiggle equals 1 over R times X squiggle. This is the equation of a line because it's Y equals something times X. So we can see that the slope would be 1 over R. Okay, so if we graphed Y squiggle versus X squiggle, we would get a straight line and the slope would be 1 over R. So for example, if the slope was 2, if you graph this and the slope was 2, then that means that 1 over r is equal to 2, which says that r is equal to 1/2 an ohm, something like that. So that's the interpretation of the slope. The slope is 1 over r. All right? To get another version, let me just, because I said I want you to linearize the graph in two different ways. It's windy here. My paper's flipping up. So let me just play around with the equation. Maybe do some algebraic manipulations. So what if I divided both sides by v? And what if I maybe multiplied both sides by r? Then I would get r times p over v equals v. So I'm taking the original equation and manipulating it. So this is the exact same equation as that. I'm just writing it in a weird way. Okay? Now what if I let x squiggle equals p over v and y squiggle equals v? Then this equation would take the form r times x squiggle equals y squiggle. This is once again the equation of a line. This is once again the equation of a line. So it's going to look like a straight line. The slope of that straight line is the number that multiplies x squiggle, which is r. All right? So we've just done that in two different ways. So I hope it's starting to make sense. Maybe I'll do a third example tomorrow. I don't know. Okay, so now let's get on to new stuff. So let me show you. By the way, could you guys make a comment for me and maybe tell me if this is streaming smoothly? Let me know. This is an experiment we never got to do. So why did we not get to do this experiment? It's because the school closed. Okay, probably I would have done this experiment the week after the school closed, but it closed. Thank you for your comments. So this is the experiment. The experiment is you have a smooth as a new jar of peanut butter. That's creepy. So we have a rope or some kind of a string, and here's a pulley, and the string wraps around the pulley, and there's a mass hanging here. Okay? So if we look at this, what we can find is that the mass that is hanging is going to control the amount of tension in this string. And in fact, if we did a free body diagram of this, you could show that the tension in this rope is equal to mg. Why is that? Because if the tension was less than mg, then that would mean that the mass here would accelerate downwards and hit the floor. Okay? So basically the mass controls the tension. Okay? Now, what if we took this string and we plucked it? So we just went, we pluck it. We pluck the string, and what's going to happen is you will excite the first harmonic. So the first harmonic will start vibrating, which kind of looks like this for half the time and this for half the time. Okay? So we would basically observe the frequency of vibration. So we observe the frequency of vibration, okay? And so we could make a data table of tension versus frequency, okay? And you can try this with a rubber band. I don't even know if I have any rubber bands in my entire house. I probably do. I'm too lazy to get up and look for one, but what you can do is you can show with the rubber band is that as you up the tension in a rubber band and you keep plucking it, so you take this rubber band, you pluck it, and you'll hear a pitch. You stretch it out, you pluck it again, you'll hear a different pitch. You stretch it out more, you pluck it, you'll hear a different pitch. So what you hear is you'll kind of hear a kind of like that. I think I'm going to have you guys do this experiment at home. Maybe next week. So basically what you would observe is as the tension goes up, the frequency also goes up. Okay? Now, this is the first, remember, when you pluck an instrument, you hear the first harmonic. So this is actually the first harmonic, and the equation for the first harmonic is V over 2L. This is a closed instrument, where L would be the length of the part of the string that's vibrating. Okay? We can take the frequency and we can multiply by 2L, and that would give us the wave speed. All right? So we can use that to get the wave speed. The wave speed would be 2LF. So basically what that gives us is a data table of tension versus wave speed. Okay? And the goal of the experiment is to figure out what is the relationship between tension and wave speed. But because we're not actually doing the experiment, I'll just tell you what the relationship is. The wave speed is equal to square root of T over mu, where T is the tension in the string, okay, and mu is the mass per length. Of the string. So that's going to be equal to the total mass of the string divided by the total length. Okay? You can see that the more mass the string has, the slower the wave speed is. That's because if the string is more massive, then it has more inertia, and so it's harder to make the string vibrate quickly. Okay? So this is today's equation. And I'll maybe have you guys do that experiment at home. If you have rubber bands lying around, I'll write something up for you next week. So let's do an example. What if we had a rubber band of stiffness K and natural length L, and mass m. Okay? The band is stretched an amount x. So remember, all right, well, I'll talk about that in a second. What we want to do is we want to then calculate the wave speed. Okay? So if you have a rubber band with a natural length of L and it's stretched an amount x, this is the distance beyond taut, remember? So what that means is that the total length is going to be L plus the amount that it's stretched. So what does that mean about the mu value? That means that mu is going to be m over L plus x. Okay? So as you stretch the rubber band, the mass per length gets smaller. Why is that? It's because you're adding length to the rubber band, but you're not adding any extra mass. Okay? So this is mu. Then we also have that the tension is equal to kx. This comes from the equation for rubber bands. The amount of the force you have to apply to stretch it an amount x is equal to kx. We established that at the beginning of the school year when we took a rubber band and we did a force versus x graph. And we saw that it looks like a straight line. Okay? So I can take these two results and I can plug them in for the wave speed. So V equals square root of tension over mu. The tension is given by kx. The mu value is given by m over L plus x. I'm dividing by a fraction, so I have to multiply by the reciprocal. So this is going to be square root of k times x plus L over m. So this is an equation for the speed. So what you can see is x is in the numerator. So as x increases, the more you stretch it, the higher the wave speed gets, and therefore the higher the frequency it gets if you pluck it. Okay? I'm not even going to bother to put in numbers. You guys can do that in the daily exercise today. So that's my lesson. I would really love to see some activity on the recipe section of Discord. I would also like to just hear if you guys have any questions on Discord, because I haven't heard from any of you in over a week. So I hope you have a really nice afternoon, and I hope I'll see you on Discord or tomorrow. Bye now.